So it's time to do some exercises. So the first one, so V Banach and W contained in V subspace. Then, so let us say closed subspace, so that it's also a Banach space. Then the weak topology on W is the same as the topology induced on W by the weak topology on V. So let us take U, weakly open set in W. So what is this going to be? So U would be of the form set of all X in W such that mod Fi X minus X naught. So this is the neighborhood of X naught. So X naught in U. Okay, so is less than epsilon, 1 less than equal to I less than equal to K, and Fi belonging to V star, W star. Okay, so this is how the neighborhood will look like. But then by the Hahn-Banach theorem, there exists Fi tilde in V star such that Fi tilde restricted to W is the same as Fi, and therefore U is equal to set of all X in V such that mod Fi tilde X minus X naught less than epsilon, 1 less than equal to I less than equal to K intersection W. Okay, so every weakly open set is a weakly open set in V intersection W, and therefore it is open in the induced topology. Conversely, if you have a weakly open set in the induced topology, then the restriction of, if you take any open set like this, okay, and then any Fi tilde when restricted to W is a continuous linear functional on W, and therefore it will work out to be like this. Therefore, you have that the weakly open sets in W are precisely the weakly open sets in V intersection W, and therefore you have that it is the same as the induced topology. Okay, so next one, V is Banach and W contained in V is a subspace. Then the norm closure is the same as the weak closure. So there is no difference between the weak closure of W and the norm closure of the W. Okay, so W closure contains W solution, and W closure is a closed subspace, and therefore it is weakly closed. So it's a weakly closed set containing W, therefore W closure will also contain W closure weak, because that's the smallest closed subset in the thing. Similarly, W closure weak contains W and it is weakly closed, implies of course norm closed, and therefore W closure weak contains W closure. So you have both inclusions, and therefore you have that the two closures are the same. 3. V is Banach and W contained in V is a subspace. then W perp is weak star closed in V star. So solution, what is W perp? W perp is the set of all f in V star such that fx equal to 0 for all x in W. So this is nothing but the intersection over x in W of kernel of Jx. Okay, but then Jx is weak star continuous. That is how the weak star topology is defined. So kernel Jx is weak star closed. Arbitrary intersection of closed sets is closed. So this is weak star closed. 4. Weak topology on V, weak star topology on V star, make these spaces locally convex topological vector spaces. So weak neighborhood in V, weak star neighborhood in V star, clearly convex. So every point has a convex neighborhood. If you just see the definition, you can check that they are clearly convex sets. So only to show addition and scalar multiplication are continuous. So but if you take V cross V, okay, so xy in going to x plus y is norm continuous, implies weakly continuous. Similarly, x going to alpha x is weakly continuous. Therefore, weak topology. So V with weak topology is a locally convex topological vector space. Okay. Now what about V star? Okay. So let H in V star, H equals F plus G. And then you take a weak star neighborhood of H. How does it look like? U equals set of all phi in V star such that mod H minus phi xi is less than epsilon, 1 less than equal to I less than equal to k, and xi are arbitrary elements in V. Okay. So now you consider the following. So you consider the following set in the product space. Okay, the weak topology because of the dual space is nothing but the product of the duals. Therefore, the weak topology on the product space is nothing but the product of the weak topologies. Okay, so now let us consider the following set of all phi in V star such that mod f minus phi xi is less than epsilon by 2 cross set of all psi in V star such that mod f minus psi xi is less than epsilon by 2. So this is a product. So this is a weak open set in V star cross W star, V star cross V star, sorry. Okay. So then you have your mod h minus phi plus psi xi is less than or equal to h is f plus g, and therefore you have mod, so this is, sorry, this is not f here, this should be g. Okay. So then you get this is less than or equal to mod f minus g f minus phi xi plus mod g minus psi xi, and therefore this is less than epsilon by 2 plus epsilon by 2, that is epsilon. Therefore this shows that addition is weak star continuous, because if you take any neighborhood you can find a neighborhood of f and g such that this is true. Therefore f plus g, fg going to f, this is the neighborhood of f, this is the neighborhood of g, and that product is contained in the neighborhood of h, and therefore addition is continuous. And similarly scalar multiplication. Therefore V star with the weak star topology also locally convex topological vector space. So I have made a remark earlier that if you have a locally convex topological vector space, then all the Hahn-Banach theorems can be reproduced, and therefore the Hahn-Banach theorems are all there. So now let us do the following 5. Z contained in V star subspace V Banach. Okay, show that Z closure in the weak star topology is nothing but Z perp perp. So if you recall, we have shown that if Z is contained in V star, then Z perp perp contains Z closure. This is the norm closure. So it, and in general you can't say that they are equal, but it happens that Z perp perp is a weak star closure. Okay. So Z perp perp is weak star closed. We have already seen this in the third exercise, exercise number 3. And then it contains Z also. Okay. So Z perp perp contains the weak star closure. Okay. So now assume that this is not equal, assume f naught belongs to Z perp perp minus Z closure in the weak star topology. Okay. So by Hahn-Banach theorem, so I told you Hahn-Banach theorem is applicable, so Hahn-Banach applicable to locally convex topological vector spaces, and therefore there exists a continuous linear functional such that continuous linear functional such that phi of f naught is not 0 and phi restricted to Z closure weak star is identically 0. Okay. So we want to get a contradiction. But what is phi? A continuous linear functional in the weak star topology, we saw the only possibility is that it is a form of Jx. So we said the weak star topology was formed in terms of the Jx's, but we later proved a proposition that every continuous linear functional with respect to the weak star topology has to be of the form some Jx. Okay. So we have f naught of x is not 0 and f of x equal to 0 for all f in Z. Z closure weak star, so in particular it is true for all Z. So this implies that x belongs to Z perp, okay, and this implies, since f naught belongs to z perp, we have f naught of x equal to 0, which is a contradiction because we assume that it is not 0. Therefore, this is a contradiction and that proves the problem. 6. VW Banach and T from V to W is linear, just linear. The following are equivalent. 1. Xn converges to x implies Txn converges to Tx. So, this is in V, this is in W. So, this is, that is, T belongs to LVW. 2. Xn converges weakly to x in V implies Txn converges weakly to Tx in W. And 3. Xn converges to x in V implies Txn converges weakly to Tx in W. So, all these three statements are equivalent. So, solution: 1 implies 2. So, T belongs to LVW implies T is weakly continuous. Therefore, Txn, Xn, therefore Xn converges to x implies Txn converges to Tx. So, that implies 1 implies 2. Now, 2 implies 3. So, Xn weakly converges to x implies Txn weakly converges to Tx, that is given. So, if Xn goes to x strongly in V, this implies Xn converges to x weakly, and therefore this implies that Txn converges to Tx weakly. So, that is just the statement 2. So, then 3 implies 1. So, what is now given? Xn converges to x implies Txn weakly converges to Tx. So, we want to show T is continuous. So, let Txn converge to some y. So, this implies Txn weakly converges to y, and the weak topology is housed off. So, y has to be equal to Tx. So, Xn converges to x, Txn converges to y implies y equals Tx. So, that means Gt is closed implies T belongs to LVW. So, all the three are equivalent. Seven. So, VW Banach and T from V to W linear. Then we saw that T belongs to LVW if and only if T is weakly continuous. So, this was a theorem which we have already proved. Okay. So, now we are going to say, show that, so A, show that T from V with the norm topology to W with the weak topology continuous if and only if T belongs to LVW. So, we are really showing that it does not really matter as far as linear maps are concerned. The continuity in the standard sense is the same, whatever other topologies you are going to put. Okay, so solution. So, T belongs to LVW. So we want to show it is continuous. So we are proving the reverse part. Okay, so we want to show that this is continuous. So let us say U weakly open in W. Okay, so implies U is norm open, and that implies T inverse of U is norm open. Therefore, T from V norm to W weak is continuous. What about the other way around? So T from V norm to W weak is given to be continuous. So to show T belongs to LVW. Okay. So let us take Xn converge to X in V, then T is continuous, therefore it implies that Txn weakly converges to Tx in W. And this is precisely statement 3 of exercise 6, and therefore that implies statement 1. So Txn goes to Tx in W by the closed graph theorem. That is what we saw, and therefore we have this implies T belongs to L. B. What happens if we interchange the topologies? So let us take T from V to W linear and T V weak to W norm continuous. So let us take Xn converge to X in V. So this implies that Xn weakly converges to X in V, and therefore that implies since T V weak to W norm, so Txn strongly converges to Tx. So this implies that T is an LV. Converse not true. So this is the only case where you have a problem. So you take identity map from V weak to V norm. So identity map belongs to LVW, LVV or LV itself. So we said but you take D open unit ball in V, which is norm open, but D is not weakly open as we saw, therefore I not continuous. I is not continuous. So you have a norm continuous linear map, but it won't be continuous from the weak topology to the norm topology. Okay, so that is 8. Let T from C0 to L1 be defined by Tx equals Xn by n square. So x equals x1, x2, xn and so on. So you take coordinate wise, I am going to define. So then T belongs to L of C0 to L1, but and T of B is not closed. So B is the closed unit ball. So it is not necessary for closed sets to go to closed sets, okay, if you have this. Okay, so let us take norm Tx. So you are taking L1, so this is equal to what? Sigma mod xn by n square, n equals 1 to infinity, and that is less than or equal to maximum of the xn's, that is norm x infinity, into sigma 1 by n square, n equals 1 to infinity, and I am sure all of you know what this is. So this is pi squared by 6 times norm x infinity. Therefore T belongs to C0, L of C0 into L1. Now you take in B, so you take xn equals 1, 1, 1, this is n times, followed by zeros. So this belongs to C0 because it is terminally 0, and then norm xn infinity equal to 1, therefore all the xn's belong to B. So now you look at Txn. Is equal to 1, 1 by 2 square, 1 by 3 square, 1 by n square, 0 and so on. And what does this converge to in L1? So this converges in L1 to 1, 1 by 2 square, 1 by 3 square, 1 by n square and so on. So this is this. So the image, so Txn is in, so T of xn belongs to Tb, and it converges to something in L1, but this is not in the range because if it has to be in the range of T, there is only one particular candidate, namely 1, 1, 1, 1, 1 up to infinity, and that is not an element of C0. Okay, so this vector is not in the range of T, therefore Tb is not closed. However, if suppose V is reflexive and W is a non-linear space, W is a Banach space, sorry. And T belongs to LVW, then Tb is closed. So what is B? Closed unit ball. I hope I said that in the previous exercise also. Yeah, closed, B is a closed unit. Okay. So solution. So T is continuous, implies T is weakly continuous. V reflexive, so this implies B is weakly compact. T is weakly continuous, continuous image of compact set is compact, so Tb is weakly compact. Weak topology is Hausdorff, so Tb is weakly closed, implies Tb is norm closed. Okay, so the reflexivity makes all the difference. Okay. Then 10. Let W contained in L1 subspace. Then W reflexive implies W is infinite dimensional. Is finite dimensional. So the only reflexive subspaces of little L1 are the finite dimensional subspaces. There are no other subspaces. Okay, so solution: W contained in L1 subspace which is reflexive. Okay, so that means BW closed unit ball is weakly compact. Okay, BW is the closed unit ball. So then any sequence in BW has a weakly convergent subsequence, because we saw in a reflexive space any sequence contains this. Converse of this was the Eberlein-Schmollian theorem. So we proved, of course, that if you have a reflexive space, any bounded sequence has a weakly convergent subsequence. Okay, so now weakly convergent means what? So xn converges weakly to x in W. That means what? For every f in W star, f of xn converges to f of x. But then this implies for every f in V star, restriction of V star functionals are also continuously linear functions in W. So we have f of xn converges to f of x. Therefore xn converges to x weakly in V also. Okay, so implies weakly convergent in L1, and by Schur's lemma this implies norm convergent. So any sequence has a norm convergent subsequence, and this implies that BW is norm compact, and that implies W is finite dimensional. Okay, so I would like you to, these are very simple exercises again, so I would like you to try it yourself. So 1 less than P less than or equal to P less than infinity, then LP is separable. We might have even used this. So all you have to do is take finitely supported sequences, that is 0 after some time, those are dense in LP, and then show that rational sequences are dense in that. So, and that finite rational sequences are countable, and that will be dense. Okay, so that is the solution for that. Similarly, C01 is separable. So any continuous function can be uniformly approximated by a polynomial, that is Weierstrass theorem. So then you approximate that uniformly by polynomial with rational coefficients. So okay, so you just have to write down the arguments correctly, and that. Okay, so with this we will wind up this chapter. Thank you.